Okay, folks, we're gonna shift into this binary vapor pressure diagram here. So still describing properties of mixtures and solutions, but now we're looking at a solution made of two volatile components, right? So we've got some container, right, containing a mixture of A in the liquid and B in the liquid, and each of those will be in equilibrium with their respective vapors. So that says A in this liquid mixture is in equilibrium with its vapor, and B in the liquid is in equilibrium with its vapor. And so that means we need to think about Dalton's law of partial pressures. So the total vapor pressure of this solution will be equal to the partial pressure of A plus the partial pressure of B, where the partial pressure of A is going to equal the mole fraction of A in the liquid times its pure vapor pressure, and the partial pressure of B will equal the mole fraction of B times its pure vapor pressure. And so now if we look at our binary vapor pressure diagram, we can see two lines here, one describing the liquid composition and one describing the vapor composition. And so if we look, so this is in reference to the mole fraction of A, and you notice here that we've got the ZA, XA, and YA. So, and I use the Greek letter chi because that's pretty standard. Sometimes we see X used as well. So Z is our mole fraction, and it's generic. X, or chi, is specifically the mole fraction in the liquid, and Y is specifically the mole fraction in the vapor. So for example, if we look at this mole fraction of 1, which would be pure A, we can see then that the vapor pressure of the solution is that of A. Or if we look at a mole fraction A of 0, that would be pure B. And so thus the vapor pressure of the solution is just the vapor pressure of pure B. And now when we mix those, so our liquid composition is described by this line, and our vapor composition is described by the curved line. So that straight line described by the liquid mixture is our Raoult's law, right, from this equation here, where we can just expand on that as we've done before. Chi A times PA plus chi B times pure PB, okay? So now what's important to note, though, if one component is more volatile than the other, and in this case, A is more volatile than B, we can see that from the graphs right here, right? The vapor pressure of A is higher than that of B. So what that means is if I look at this liquid composition given by that point right there, right, if I follow all the way down, that's given by chi, or X, right, the composition of the liquid. We can see here that the composition in the vapor will be enriched in A because A is more volatile, okay? So now if we keep playing with that idea, so here now I'm only showing the vapor lines. So let's note that's the vapor composition. And we noted here that if we think about this more carefully, right, the mole fraction of A in the vapor is going to equal the partial pressure of A over the total vapor pressure. So I'll write P vape to be consistent with how I wrote it last time, okay? So, and then of course, the composition of B in the mixture will be the partial pressure of B over the total vapor pressure of the liquid. So we also noted that P vape is going to equal chi A times PA star plus chi B times PB star. And noting that chi B will equal 1 minus chi A, we can plug that in to this expression and just do some algebraic rearrangement. And I'll just do that for you right here. So that ends up being PB star, the pure vapor pressure of B, plus PA star minus PB star, so the difference in pure vapor pressures, times just the mole fraction of A. And now remembering that PA was chi A times PA star, we can get an equation to describe the composition in the vapor as the following. That will go as, let's see, chi A times PA star, all divided by P vape, the total vapor pressure, which is just PB star plus PA star minus PB star, all times the mole fraction of A in the liquid. So now what these numbers are telling us right here on this graph are the ratios of A and B in our mixture. So this number 1 right here, I'll point out to, that corresponds to the vapor pressures of A and B being identical. That 2 corresponds to A being 2 times as volatile as B. The 4 is A is 4 times as volatile as B. And so you can see the more volatile A is relative to B, the more curvature there is in this, and thus the more enriched A will be in the vapor relative to B. And again, given that A was the most volatile component. So now we can also be somewhat quantitative with these diagrams. So I'll redraw this thing where I've got P versus mole fraction. And I'm going to zoom way into like a region close to the liquid vapor boundary. So this is not by any means like spanning a full mole fraction of 0 to 1. But noting here, like if I pick this arbitrary point, okay, that corresponds to the liquid composition. And now for this lever rule says I can draw a straight line over, which is called a tie line. And now I can drop that straight down, and that's my composition in the vapor. And now using the lever rule, it states the following. If I now pick some arbitrary, or not arbitrary, but some point that's exactly halfway between these, okay, so halfway between, then we're able to calculate specifically how many moles are in the vapor by the following. So we can say that the length of this line, I'll give that as, I'm going to use L, and I know it gets confusing, so I'm going to say LL, so that will be the length of the line in the liquid. LG is the length of the line in the gas, so just arbitrary, like whatever that value is in mole fraction. And that's going to be proportional to the number of moles in the liquid and the number of moles in the gas. So if we work through some math there, we could prove that the number of moles in the liquid times the length of that tie line equals the number of moles in the gas times the length of that tie line. So thus we could, by measuring those values on our graph, we could work out exactly how many moles would be in the liquid phase and how many moles would be in the gas phase. And here's a better picture of that. So like, for example, if I was looking at this A1 liquid composition at this particular pressure, so we could see that A1 prime would be the composition in the vapor. And now, of course, if I were to pump on this material, so let's suppose I was boiling this stuff under vacuum, so doing vacuum distillation, as I continue to lower the pressure, I could continue to lower the amount of A in the vapor, right? And I could keep doing that all the way until I've completely distilled all of the A out of the mixture, and I'm left with pure B. So that's kind of cool. Okay, so next up will be temperature composition diagrams and learning goal 8. I'll see you then.